Good afternoon. My name is James Murray. I'm the program manager at Orbital Marine Power. Orbital Marine are hosting the second in a series of supply chain events as part of the Tiger project this afternoon. Before we get started, I just wanted to run through briefly the agenda. So firstly, we'll have a short introduction to the Tiger program from myself. Following that, then we'll have a presentation on opportunities specifically around steel manufacturing from Orbital Marine Power from my colleagues there. We'll move on then to Fraser Johnston at CIMIC Atlantis, who will be giving some insights into lessons learned associated with volume manufacture associated with their AOR series of tidal turbines. And finally, we'll hear from Raphael Coquet at HydroQuest, again, regarding steel structure, industrial opportunities associated with their technology, and design optimization and collaborative opportunities with the supply chain there. We'll see how we go for time, but hopefully we'll have about 10 minutes. 10 minutes for questions at the end. Just to point out, we have in Zoom, there's a chat functionality you'll see at the bottom of the screen. If you want to raise anything throughout the webinar today. I'd also like to point out there's also a Q&A, a questions and answers functionality as well at the bottom of the screen. And we'll be monitoring that today to collate any questions you might have for either of the panelists today. Hopefully at the end we'll have, as I say, about 10 minutes for questions, but we'll try to get back to you on any questions you have by the end of next week. Finally, just to say, the entire event will be recorded and put up on YouTube, and there'll also be a link on the Interreg Tiger webinar or a website page to the webinar if you can't stay for the full 90 minutes, or if you want to provide a link to your colleagues. So I think that's everything for now. I will just kick off now in a moment with a brief overview of the Tiger program. Great, so you should be able to see the Tiger presentation now. So the Tiger Tidal Stream Industry Energizer project is a project specifically focused on tidal stream energy. It's, one second. It's a 45 million euro project. It's one of the largest ever awarded by any Interreg program, funded by the Interreg Channel program. It's a collaborative program really focused on acceleration, commercialization, and cost reduction around tidal stream energy, with a particular focus on the Channel region and making the Channel region really the center of a hub of activity and development and acceleration of tidal stream energy within Europe. So we've got 18 partners in the consortium. We've got 6 of the leading tidal technology developers in Europe. We've got a number of sub-projects that the program is liaising with. We have 6 universities involved, 2 regional agencies, and a number of other industrial partners and research institutions also. We've got very good representation on both sides of the channel, and we have a number of other strategic partners that are involved in the program from out with the Channel region, but who are hoping to help stimulate and enable the sector within the Channel region. The entire project is led by the ORE catapult. That's the Offshore Renewable Energy Catapult. And for those that aren't aware of it, the catapults were a UK government initiative really to bridge the gap between industry and academia and technology developers and technology challenges, really to sync it all up to more efficiently address industry challenges. And so ORE is the offshore renewable energy catapult for the UK, specifically responsible for marine energy and offshore wind. So there's no better organization really to lead what is a very much a collaborative initiative between industry, academia, and research organizations and development partners to stimulate the acceleration of the sector within the Channel region. So moving on to some of the higher level objectives and aims of the project. So there's, as I say, there's a number of partners involved in the project. There's a number of developments being progressed in the project, both project developments, research developments, and a range of other initiatives. But at a very high level, what it's all about is if you think of it in terms of the cost of energy, of tidal energy generation, the overall aim is to reduce that to around 150 euros per megawatt hour by 2025. And there's a number of things we need to do to achieve that. First of all, we need to see accelerated volumes of deployment, of testing and first array projects within the Channel region. So we've got a number of full-scale tidal technology developers involved in the consortium, and we need to see more deployment of those technologies so that we can accelerate learning associated with those deployments and engage with the supply chain around volume and scale manufacture. So a big focus on site and project development and offshore testing and all the learning associated with that. The second strand really is focusing on the technologies, focusing on significant reductions in levelized cost of energy. And on the capital cost side of things, that's around equipment, it's around components, around all the innovation associated with them. It's also associated with scaling those components and very much looking at the processes and the manufacturing processes around developing those components to reduce the cost of those components as well. On the operational side of things, then, a big focus on offshore maintenance strategies, operation logistics, informed by real-time data on component reliability, on weather risk, and on all of those sides of things, again, with a big focus on the other side of the levelized cost of energy equation of reducing and minimizing operational costs. And then finally, in terms of some of the more commercial considerations, there's a big focus reaching out to financiers, to insurers, looking at ways of increasing project debt into first commercial arrays, I suppose reducing the cost of project debt, reducing the equity risk associated with those technologies. So as the technologies mature, as generating costs come down, we need to see that the cost of capital and influx of capital into the sector doesn't inhibit the growth and acceleration of the sector. So then just moving forward to some of the specifics in terms of the sites that are being developed in the project, we've got very good representation from both sides of the channel. I mean, to put it in context, there is the potential for over 4 gigawatts of tidal stream capacity within the Channel region alone. So a huge potential for a whole new generating sector. We've got representation from all the main tidal resource regions, from the Rab Blanchard and the Gulf of Morbihan, and Pampo Breha on the French side. We've got representation associated with PTEC on the Isle of Wight. And we've also got, as I say, other strategic developments such as Ramsey Sound out with the Channel region, but very much a very important part of the overall program that are also carrying out activities and testing within the project as well. So within the project is a target for up to 8 megawatts of deployment within the project, which would be very much a success because it's a reasonably short project, and so to consent projects, to build machines, and to commission those projects, and 8 megawatts would be which would be a great contribution towards accelerating the sector. But following on from that, then a huge potential to consent further sites and see further deployment of arrays after the project has completed. As I said then, a big focus on cost reduction in work package 2, and we want to very much work with supply chain companies on those cost reduction. And finally then in work package 3, pulling that evidence case together, taking all the learning from the multiple strands of the project, both in terms of the developments, the cost reductions around R&D and innovations and components, pulling that together into a compelling evidence case for policy support for tidal stream energy within the EU. So as I say today, at a high level, the consortium is working on over 46 different equipment designs for tidal stream energy. We don't want to do that in isolation, so we want to reach out to the supply chain on those designs and those processes associated with them to reduce the costs associated with them. And that's one of the key reasons for this webinar today, is to reach out, tell you a little bit more about what we're doing, so we can think about potential collaborative opportunities with the sector. So thank you very much. I'm now going to introduce my colleagues at Orbital Marine Power, Mark McCarthy and William Annell, who are going to present on steel fabrication and engagement opportunities with floating tidal technology, and specifically with the orbital floating tidal technology.
Hello, everybody. Yeah, hopefully you can hear me. And my name is Mark McCarthy. I'm the Operations Director for Orbital Marine Power. I'm speaking to you from our assembly factory in Dundee. I'll be co-presenting this with my colleague, William Annell, who's Head of Mechanical and Structural for Orbital. Just making sure I can actually... I've been with Orbital Marine Power just over 2 years. My role is to act as the project manager for the O2 turbine, but the company was founded some time ago. So I'm going to pass over to William here, who will explain the company history from 2002.
So my name's William Annell. I'm the Mechanical and Structural Engineering Manager here at Orbital. And I'm presenting from our headquarters in Kirkwall, Orkney. So Orbital Marine has been in existence as a company since around about 2002. Our first incarnation was Scott Renewable's tidal power. So in the early days of the company, it was like a number of other small R&D organizations. We were around about 12 employees. And really the focus of the company at that stage was to develop the concept and remain small while we made lots of mistakes, trying to figure out the fundamental issues before moving to a larger scale. So there was a great focus on research and development, tank testing, developing numerical models, trying out different concepts before getting larger and larger. So this included tank tests and sea trials, and really helped form a great deal of confidence in what we were doing with regards to floating tidal. All this work allowed us to progress to doing our first large prototype. It's a 250 kilowatt device that we launched in 2010 and connected to the grid in 2011. That particular machine weighed around about 100 tons. So it's still quite small by the scales that we're really needing to bring down the cost of energy. We did a lot of work with that machine. It was a quintessential prototype. The basic function of the turbine was just to prove that you could harness energy from a floating structure and put it into the grid, and it certainly did that quite well. But probably the biggest benefit for us was it helped us develop our marine operations procedures and prove our access and maintenance philosophy as well. All this work gave us the confidence to move to our first, we'll call it commercial scale demonstrator in 2016. I'll speak a little bit more about that in a couple of slides' time. So we had started off as a small R&D company. That was actually back in Stromness, but since then we've grown after a couple of major investment rounds to have an office in Edinburgh. The headquarters is still in Orkney, which is placed right next door to the European Marine Energy Centre. So we're right on the doorstep of where we're conducting our sea trials and exporting energy to the grid. There's around about 33 people in the company now, and we've accumulated over 100 years of engineering experience. Now, probably the biggest achievement that we've had to date is exporting around about 3 gigawatt hours to the grid in 2000 and I think that was 2016, 17. Now that was a world record at the time for floating tidal energy, and that really was the final cherry on the cake that sort of proved that you could operate and generate to the grid for a consistent period of time. But if you actually look at the energy generation graphs throughout the year, it's not entirely stable. It doesn't start off and then just go straight up. There was a period of commissioning during the early days, but then after the commissioning phase, the energy that we produced ramped up and was fairly consistent. But during that period, we were still able to carry out maintenance interventions without disrupting our production capabilities. In 2018, we rebranded to Orbital Marine Power, and shortly after, we carried out a crowdfunding exercise where we raised about £7 million, which was the UK's ever largest crowdfunding exercise. Now, the sum of money was quite large, but also the number of people that signed up to the bond was also quite large. I think it was about over 3,000. I'm not sure the exact number, but I think it was over 3,000 people. And the range of contribution was quite a lot, but there was a significant number of small contributions as well. So it was quite a broad spectrum of people that really believe in the concept, which was a big boost for us as a company. So in 2019, we started the construction of the O2 device, which is it's another 2 megawatt machine. After going through a fairly large tendering exercise with a number of different fabricators. Okay. So what's the main objective of Orbital Marine? So James kind of introduced the overall concept of the Tiger project, which is commercialization, bringing down the cost of energy. We're aiming to sign up to the general goals of tidal energy, which is producing millions of power for homes, business around the world, but power that's predictable. And we're going to do that with our proprietary technology, which is a floating superstructure with 2 rotors that hang underneath. So there's a couple of different incarnations of our technology, but we believe that this is the way to do it, with a single floating superstructure that allows for maintenance intervention to be carried out relatively cheaply and quickly. So I'd alluded to our first breakthrough project in 2016. So this was, at its time, was the world's largest tidal turbine at around about 2 megawatt rated. So there was 2 1 megawatt nacelles, each with 16 near rotor diameter rotors. For that particular device, we had stall control rotors, so variable speed rotors that allowed a relatively simple PTO within the nacelle, rather than moving to variable pitch. which we believed at the time was a step too far in terms of development. We didn't have the resources at the time to develop a pitch system. There was plenty other challenges and problems to solve before getting to that stage. So the SR2000, or SR1 2000 as it was rebranded, was a 500-ton machine, and the hull structure is formed of sub-arc welded cans. So it's a tubular structure that is fairly well suited to automated growing line processes. The leg structures underneath are beam structures in simple terms, but it was all a fabricated structure, and the same with the nacelles. The tube structure, I think, weighed around about, I think it was about 230 tons, and the legs were around about 20 tons, and the nacelles were around about, just the steel work was around about 15 or 20 again. So, Mark, do you want to talk about a little bit of construction philosophy?
Yeah, move on to the actual cross-section of the turbine. As William said, the key here in terms of manufacturing was to obtain a design that worked for the supply base. With the work that the team had already done on the SR2000, we knew what diameters would work for our various suppliers in Scotland. So we kept effectively the same hull diameter. And William and the mechanical team had done the design of the turbine in accordance with its structural integrity, what was required to meet the objectives of 25-year life cycle. What we were able to do then was to develop a construction strategy for the fabrication of the O2 turbine. We broke it down into modules, in effect, and went out to talk with the supply chain about their capabilities. So we were trying to match the capabilities of the supply chain within Scotland and the UK to the capabilities and the engineering requirements of the O2 turbine. So what this meant basically was to understand what the craneage, what the door width, what transportation requirements were for the various suppliers, so that we could optimize the size of the individual components for their manufacture. Certain elements of the O2 were fabricated and manufactured in-house. The blue elements that you can see on the slide there were actually our own design. We actually manufactured those skids in our workshop in Orkney, but the fabrication of the steel skids underneath was done locally up in Thurso. So it's not just the large fabrication of the structure, but we've also got a large amount of smaller fabrications, both within the turbine itself and also out with the turbine. A good example of this is on the screen at the moment. This was done by competitive tendering and was manufactured on the island of Anglesey by a company called Fawn Trackway. These are 4 anchor baskets, gravity baskets, that were fabricated in Wales. So the design again gave us flexibility to go to various suppliers, both in Scotland and the UK, to enable to get a competitive price. So moving on. But when we come back to the larger fabrications, as William said, we have a structure that requires to meet the engineering integrity. So William, if you want to explain how we decided to split the turbine down into the various sections.
Yeah. Okay. So yes, Mark pointed out there the whole strategy behind the design and the tendering. The way that we broke it down was to try and avoid limiting ourselves to one particular destination, so we could cast the net as wide as possible. So with the superstructure for the O2, we broke the superstructure down into 4 chunks that were all within the road transportation limits. So the width was considered, the weight and the length of each section. This also applied to the legs and we've also considered it for the nacelles as well. Now, this allowed, I think, a good number of different people to have an opportunity to get involved with the rolling of the cans, the fabrication of the legs. The fabrication facilities can be inland or coastal. We haven't been limited to just having large quayside facilities. One of the main considerations that we had early on in the design process was draft. So the SR2000 had a draft of around about 6.4 meters, and that was with the rotor legs retracted. With the O2, we've managed to reduce that to around about 3 meters. So by doing this, we've opened ourselves up to dozens of facilities up and down the UK, that really gives us a lot of flexibility for doing this particular machine. It's the project. We have to acknowledge it's a one-off. So it might not be suited to somebody that has a very large facility and somebody that's very busy, who can deploy it with relative ease. Whereas by doing one-off and allowing ourselves facilities with a lot lower draft, lower depth at the quayside, it fairly opened things up. Everything that was kind of into the design was all kind of standard steel fabrication grades and welding techniques that many fabricators around the UK will be familiar with. The codes we use are very common in oil and gas and in shipbuilding. We try and design so that things, when a fabricator looks at a set of drawings, they understand the drawings, and it makes sense to them. And if it makes sense to the fabricator, that probably means that you've made some good engineering decisions along the way. One of the big learning curves that we had from the 2000s, so we had a lot of input in the SR2000, our first large prototype, in the fabrication. So we got really detailed look at some of the issues that can arise from the poor design choices early on. So with the O2 structure, we've tried to avoid complex welding operations, dissimilar grades of steel. All the steel uses, I think it's just like probably two or three weld procedures at most throughout the whole structure. Space and access requirements for welders. We've really tried to make lives easier for the welders, rather than avoid people going into a horrible cramped space with poor access, because all that does is it costs money, and it just creates an opportunity for more weld failures, which can cause severe disruption in the build process. You really just want to avoid it from design, rather than having to rely on the best welders and luck as well. So all this work, I'll let you kind of go into a little bit more about the contract sample smart.
Yeah, obviously what we needed to do, in addition to standardized techniques, as William's explained, we also went for standardized contracting, went for an oil and gas type contract that people were familiar with. And the net effect of casting the net wide and standardizing the design and using techniques that people were familiar with is we ended up with a very wide supply base within the UK. A lot of Scottish content, great fabrication, Texo here in Dundee, but we've also got contractors as far afield as Gosport and Anglesey. So basically, UK supply chain is very well represented on the O2. Some pictures of the various steel fabrications in manufacture. You can see William there adding scale to the size of the cans on the bottom right. But we've also employed European contractors. The powertrain, which sits on the end of the legs, is actually manufactured by one of our partners, SKF, manufactured and assembled. So they've got components coming from Sweden, from Germany, Czechoslovakia. And I'm glad to say, actually, all of the components are all moving around Europe now, heading towards Germany for assembly in a manufacturing plant near Schweinfurt in Germany. So all of these components were supplied under one major contract with SKF. Yeah, you can see an example of some of the components courtesy of SKF. We've got the gearboxes, top left, and the gearboxes arrived in Germany fully tested. And again, some components which have now arrived in the assembly hall in Germany. We've got the main shaft unit, which has been assembled and tested and has arrived in the assembly hall. You can see on the right-hand side an example of fabrication from one of our German colleagues. They are manufacturing the nacelle fabrication in Germany for SKF. So individually, when we're developing a single turbine, that brings obviously capability and capacity into focus. But when we move towards larger volume, then obviously the problem becomes a little bit bigger. It basically becomes a space problem. So in addition to the components being quite often at the maximum capacity of some of our suppliers, they're also very large components. So one of the things we need to think about is how can we safely get large volume through our supply chain. So you can look at the number of tidal arrays, look at the number of turbines, estimate how you would break that through into components in a similar way as William's described. We'd need to look at the technology to see if certain suppliers have different breakpoints within the design. So we may have to alter the way that we manufacture certain turbines to suit the manufacturing cycle. But basically we will use the O2 design and the supply chain for the O2 as an example of how to do best practice. And then we'll look at the volume question as a second issue. So we've done a study looking at the high volume with our partners, Black & Beach. So again, what we need to do is obviously understand the political funding assumptions within the model, which gives you a geographical net in terms of where the supply chain will be sitting. And then we're going to need to go out and engage with the supply chain at every level to understand their capabilities, their capacities, and the space available. We also need to clearly understand the timing and the schedule relating to various turbines, particularly when we get into large numbers, and literally just spend time with the supply chain, go out and talk with them, explain to them the size and nature of the components and the volume, and then we can hopefully develop a plan that works both for the multitude of turbines, but also for the supply chain. The key issue for us is steel fabrication. The O2 turbine and the SR2000, before it was designed specifically as a steel fabrication. The engineering that William and the team have done enables us to break the turbine into different sections so that we can do modular assembly, and that hopefully widens the number of fabricators that could engage with the process. So we may end up to meet a multitude of orders having a multiple supply chain supplying the same parts in different places, and that'll all have to be assessed in terms of capacity moving forward. So it's a large exercise yet to be undertaken in terms of high volume supply, but we think we made a good start understanding the O2 supply chain. And that concludes the orbital presentation. Thank you.
Great. Well, thank you very much, Mark. And that was really informative and hopefully giving people food for thought. I just like to remind any of the attendees today, if you want to post any questions that come to mind throughout the event, just to put them into the Q&A functionality at the bottom of the screen. And now we can move on to Fraser Johnson from CIMIC Atlantis, who's going to discuss the AOR series of tidal turbines that they've developed.
Good afternoon. Thanks, James. Hopefully you can now all hear me. So yeah, I'm just going to take you through the AR series turbine. This is a system that's been installed now at the Maygen array up in the top of Scotland since 2016, 2017. So just on your screen, I just wanted to provide for the audience just the difference between, or some differences between the two turbine systems. So the AR series turbine, the Atlantis turbine that we have at Magen, along with the Hammerfest turbine, they are seabed mounted units, horizontal axis, similar to the orbital turbine. 3 rotor blades. It sits on a seabed foundation. In this picture, in this infographic, it's a gravity-based structure, but they can also be monopiles. But effectively, the unit sits on the seabed under its own weight, in about 40 meters of water on the Magen site, and then literally converts the flow of the water in the same way as a wind turbine, effectively. So the main unit for the AR series, it's a 160-ton unit, designed to be installed by standard offshore construction vessel, 250-ton active heave compensated crane, that kind of size. In the Atlantis design, the main body forms the main structure, so it takes the main load path rather than having an integral frame to take the loading. Modular design, so in this one we have the blades on the right hand side, then a cell in the middle which houses pumps, motors, that kind of stuff, yaw drive underneath, and then a stab into the foundation. On the back we have a generator and gearbox, and on the back of that we have the IO pod where all the controls and instrumentation sits, and beneath that we have the turbine support structure. For the Atlantis turbine, it's all wet mates, so the turbine is installed and recovered in about 25 minutes. No dry mates, so straight interconnection. The AR series really started design back in June 2011 with an installation into EMEC, and that was a 1 megawatt unit, 150 tons, and again fixed pitch. Didn't need to use the pitch system at that time. We were proving they were proving other elements. And then along came the Magen project. So within that we have 1 Atlantis turbine and 3 Hammerfest turbines. Not the world's first array, that was Nova Innovation up in Shetland back in 2016. But the AR 1500 is a 1.5 megawatt unit, again 150 tons, variable pitch, and a yawing mechanism. So it actually rotates to face the oncoming tide on every slack tide. As I mentioned, we also have Andritz turbines, so just to show you the comparison or difference between two. They're still horizontal axis turbines, but just 2 different slight variants from 2 different suppliers. So here we have 3 Andritz turbines. They are more akin to an offshore wind turbine. So they are an external shell keeping the water out. And then they have a frame, a load frame on which all of the equipment sits, torque isolated. So standard generator, standard gearbox, and a water cooling system. So unlike Atlantis, where the exterior hull of the structure is the exterior hull of the generator and gearbox for cooling. This is forced ventilation, or forced cooling. So I'm going to take you through the main components of the turbine, the main modules as we call them, and highlight areas, structural elements that we buy in, and then kind of identify where we've engaged with the supply chain, or Atlantis have engaged with the supply chain with regards to the components, to the main nacelle, the yaw, and so on. So the nacelle itself, it's a 20-ton cast lower section and fabricated top section steel structure, bolted flange on both ends to take the generator and gearbox on one end, and the slow speed shaft on the other. So the photograph in the middle was from, it must be going back to June 15 now. That was at the Nautilus facility down in Blythe, a test bed owned by Catapult. That was where the unit was put together and then tested before coming on stream and being supplied into Magen. But effectively it's a steel structure, nothing overly clever. The AR 1000 unit was all fabricated, rolled steel and fabricated, whereas this one is a lower section is cast. And that's really to take cost out. We have, going forward in a 2 megawatt and a 3.5 megawatt unit, that certainly looks at the entire unit being cast, and engagement with supply chain around how that would be done and how that could be done here across Europe or further afield. Then we go on to the gearbox and the generator. So in the AR 1500 at Magen, we have a permanent magnet unit for the Atlantis turbine, and then we have a squirrel cage induction generator for the Hammerfest. but it's an integral gearbox generator. This came out of the Switch over in Finland. 17-ton unit, and 32-ton unit for the gearbox and generator. And then the slow speed shaft, which is a 13-ton unit, forged steel unit. Again, basic manufacture, forging and then machining to take the slow speed shaft. And the slow speed shaft and the generator are actually so long, and the nacelle is also so long to balance the weight of the structure. So on the front, you've got the blades, and you've got the yaw drive and the hub. And of course, on the back, we have the generator and gearbox, and that balances the unit for lifting and also for below water for sitting on top of the structure. So there are some details as to why they are so large. We've looked at making the nacelle smaller and making the entire package smaller, which is possible, but brings in other operational considerations. The stab, effectively a large bit of cast unit. The individual cast structures, so the turbine sits on the seabed under its own weight. It doesn't have any bolting or connection mechanisms. The top design is the unit from the AR1000, which was installed in early part 2011. Castellations stop the rotation, take out the rotational torque, and then there are two bearing faces within the stab which take out the moment loads. Very similar to the AR1500 in its design, though its kind of configuration was quite different in the AR1500. That unit itself had a lot of integration with the connection management system for the wetmates. So as the turbine is installed, the wetmate connection system automatically docks passively. There is no secondary actuation. So you can install the turbine and go live within a couple of minutes. You know that your connections have been made, which makes offshore operations very swift and very, very easy. VPS, variable pitch system. We've been around a number of them actually. Hydraulic, screw jack. But effectively a large prefabricated unit that comes in, pintles for the blades, and then that is bolted onto the structure, onto the nacelle in an assembly facility. So all of the units themselves for this AR1500 came into Blythe, and the unit was assembled in Blythe. There's current turbine being assembled in NIG that will go to Japan middle of October. And again, it's the same situation or same process, that all the components come into NIG. The units are assembled in NIG, then they will be shipped out to Japan on a ship and then installed out there. Coming across to the blades of the structure. So initially back into the AR1000 GRP construction. So molded construction, these were actually fabricated in China originally. And then a test bed was fabricated by Atlantis. Again, we're going back to 2010 here, so almost 10 years ago. So testing the blades, deflection, loading and information, to really understand the characteristics of the blade with regards to our financial dynamic models and tidal bladed models, and also then taking that information forward into the next generation. These blades, as it indicates there, they are actually going to Japan. They've got a second lease of life. So they were operated in EMEC for about 2 years, and they'll now go out there and they'll operate on a 500 kilowatt unit for a demonstration unit for a number of years out there. The Atlantis turbine, these are carbon GRP. They're 8 meters long. They're now being progressed towards a 26 meter rotor where the blades will be about 12 meters long, pushing up towards 3 to 3.5 megawatts. The units we have here with Atlantis being GRP, the Hammerfest turbines that we have are actually steel. They are preformed steel, bent and then welded onto an internal rib structure. Time will tell which one is applicable for operation. They have pluses and minuses across the 2 different types. But within the Atlantis design philosophy, very much going down the carbon GRP route, looking on this turbine and moving forward. So the turbine you see there on the right, that's come out of the water there after about 2 years of submerged operation. And we use non-emitting biocide, so silicon-based antifoul on the blades. And then the main body just has a coating of epoxy paint and anodes. Foundations. The two different types or two different turbines that Atlantis have done and the 4 turbines that Magen have done in the inner sound, they've all been based on gravity-based structures, primarily for cost and risk. The first unit went into EMEC and had to be decommissioned after it had finished its operations, which was about 10 years actually. And the units going into Magen, again, they were 25-year design life, but installing large monopiles in a high flow tidal environment had never been done before. The jack-up vessel there you see is the Neptune. That was the first time anyone had put a jack-up vessel into this kind of environment and then actually conducted construction works on it. A lot of work was done to engineer that process and to make that process safe. But effectively, the foundations that we have at the moment are 230, 250 ton structures. And then we plonk 400 tons on each leg. So they soon come up to 1,400 ton units. Going forwards, we know that that's not economic, and we know that we have to go away from gravity-based structures and moving into monopiles, but that brings questions around installation process and work to be done with the likes of DEME here and GOC as to how that would actually be achieved. To give you an idea of the monopile, so we're talking about 2.5 to 3.3 meter diameter. The largest we've seen is around 4.5 meters, depending on the sites and depending upon the geotechnical information we get from the seabed. About 25 meter in length, wall thickness, 60 to 80 millimeter diameter, but rolled steel, nothing unusual, nothing too complicated. And then installation with jack-up vessel, drilling and the like to put the unit onto the seabed. We've talked about reducing the cost of energy, and one of the aspects that we certainly see within Magen and Atlantis certainly have been following is it's kind of following the wind model, where you reduce the number of systems to reduce cost alongside reducing the materials, knowing your loads and knowing your forces, understanding your fatigue life and putting material where you need it and taking it away from other areas. So one of the ways in which we see the technology progressing within the Magen array, all of our converters are onshore. So any routine maintenance we have to do on the converter or the cooling system for the converter or our switchgear is all done on a shore-based system at Ness of Coys. And at Magen at the moment, we have individual cables for each of the turbines. The way in which we see that going forward is certainly work that's been done by GE down in Rugby, multiple turbines to a subsea hub, and then individual cables to a common transformer, a common converter and transformer on shore. So that removes a lot of your offshore cabling. It removes a large number of converters and takes it down to one, and just makes the number of systems in the offshore operations is much reduced. So the subsea hub you see there on the right was installed 28 days ago. That's now on the seabed at Magen. That's now operating in conjunction with the Atlantis turbine. It's a proof of concept, proof of demonstration. We know we can put things on the seabed, but on the orange elements you see on the right and left-hand side, that's the wet mate connection system for the turbine. So the subsea hub is linked to a dry mate to the export cable, but you have the ability to interconnect export turbines without doing dry mates. So we have a lot of wet mate connection in there. Design water depth 100 meters, design life of 25 years. So it's kind of a short presentation on this one, but overall, looking at the kind of components that we see within the system for Magen, or for the Atlantis turbine, you really have the nacelle, which we know we can make better, and with interest and input from the supply chain, developing and building that, we know we can achieve. We've already looked at the different size the structural size, frame size, if you like, between the current 1.5 and going up to a 3.5 megawatt turbine. Blades get bigger, loads get a bit larger, so the nacelle will increase in size a little bit, but we don't expect it to get appreciably larger, having done all that work already. Pitch system, again, steel castings and additional components are in there. Blades, GRP, carbon, have designed and built those blades. That was done with the composite lab down in Bristol. We know there's work there to do on volume manufacture. Your drive, again, it's a drive system, mechanical seals, castings and fabrications and additional components. Nothing, it's volume manufacture. There's nothing really complicated in that structure. The stab is probably the largest unit that we have. This is steel casting. We know we can do better there. Those units was a one-off for the first AR 1500, and we know there's improvements to be made. The subsea hub, steel structure to tube, put on the seabed, so nothing very complicated. Could be a casting, certainly when we get a bit larger, to try and reduce some cost, but it doesn't have to be. And then the biggest one for us, the biggest saving, is probably the monopile foundation. Taking a 1,400-ton steel structure down to what's probably going to be less than 100. That's probably the largest steel saving we have. However, installation cost probably goes up because then we have a jack-up vessel rather than a DP activities around that. But there are benefits and losses. The last thing I have for you is just an infographic. Excuse that infographic by death on this one. So on the left-hand side, we have the Magen project, which is really 4 units. It's the world's largest array, second in installation to Nova. We've now got about 81,500 hours on the clock for those turbines. We've now put 33 gigawatt hours of power into the grid, and we continue to do so. And just to give you a comparison, 33 gigawatt hours is more power than Tidal, Stream and Wave have done across the world to date. So we more than doubled that number. The array cost 51 million at the time. It was an expensive project because of what it was. It's a Pathfinder project, helping the industry move forward and helping the industry understand its risks and its problems, and helping the industry really showcase what it can do as predictable power. Give you an example, the turbines last month and certainly over the last quarter have generated power at an availability above 97% across the array. So we know what power we're going to get, 90% availability. We know what's going to turn up. The tides are very predictable in that fashion. So Magen Phase 2 is progressing. We have already got consent for another 86 megawatts in total, so another 80 megawatts can be installed. And looking forward to the next, hopefully, CFD round where we can actually make a difference and make a bid on reasonable footing. Within Tiger, we have the Alderney Race project, which is 4 turbines, 12 megawatts, so 3.5 megawatt units offshore, 12 megawatts onshore. Then a subsea hub and a cable onshore. That project is working through Tiger to consent the site. So that's already been consented by Alstom some years ago. And that's consent is being transferred to Normandy Hydrolien, which SAE is a joint venture partner of, looking to use Atlantis turbines. And then the final one that I've mentioned is the Goto project. So this is a 500 kilowatt demonstration unit, which is a precursor to hopefully an extension of that contract, looking to install or upgrade that unit to a 1.5 megawatt unit. And this is demonstrating Tidal in Japan and really demonstrating that the technology can work and it has the reliability and availability that we say it does, or Atlantis says it does. I think that is it for me. So slightly quick, slightly whistle stop. Thank you very much for your time.
That's great. Well, thank you very much, Fraser, for that insight into the R series. And I noticed quite a lot of opportunities there for both steel fabricators, casters, and obviously composites manufacturers as well. So it's really interesting. So I'll hand over now to Raphael at HydroQuest to give us an overview of their Tidal technology and opportunities for engagement with the supply chain as well. And again, I just remind people to continue to add questions, some good questions coming in through the Q&A portal at the bottom of your screen. Thank you.
So, hi everyone. I'm Raphael Coquet, Tidal Project Manager at HydroQuest. This final session is about the industrial opportunities on HydroQuest Tidal turbines. First, I will present you our company, then our first Tidal project, which was deployed last year in Pampeluna site in France. And the next generation, which will be deployed in coming projects, and the associated industrial opportunities. So, as for Orbital and Atlantis, HydroQuest turbine uses hydrokinetic water flows from tides. And we have a proprietary design with vertical axis technology. So as you see in this picture, we have two vertical counter-rotating columns with 4 rotor in total. And so this, in fact, this design benefits from over decades of expertise. We gained in at the beginning in river deployment, but also in testing in marine application. So the main thing with our design is we have no yaw, no pitch. So we don't have actuation mechanism so it's ensured to have a robust and reliable turbine. For your information, HydroQuest is located in France, in the Grenoble area, because in fact we have quite a lot of know-how and knowledge in hydropower industry, and the company was created now 10 years ago. So from our creation, at the beginning, our main activity was to design and deploy hydrokinetic river turbines. So we deployed our first one in 2013, and then we started to look at tidal industry in 2014 and signed a partnership with Cement Shipyard. I will have some more detailed description on this later on. On 2016, we launched our main project in our tidal development, which is named Ocean Quest project, and which objective was to deploy our first marine turbine. And this first prototype and turbine was deployed last year in Pampeluna area. So at this time, HydroQuest is operating only in France, but we have intention to take our technology worldwide and are currently investigating some potential location around the world in the main tidal turbine sites. So we want to start with France because we have our facilities and first industrial partnership in France. So our first step is to deploy some tidal array in France to validate and validate our design and to optimize fabrication and supply chain and so on, and then to deploy in the main tidal sites in the world, so mainly in UK, Canada, and Asia. So the focus in France, so the two main sites in France are La Blanchard site, which is located near Cherbourg, and there is also the Frommer site. So the resource at La Blanchard is 3 gigawatts and is 500 megawatts in Frommer site. And you can see on the map the Pampeluna test site in the middle in the Channel region. Regarding supply chain strategy, so we have a major partnership with CMN Shipyard, which is our main partner for production and supply chain. It's located in Cherbourg, in Normandy, in France, so really close to Blanchard site, around 30 kilometers. It's quite a large shipyard, so it has the perfect size for the design of our turbine design, and so the really good production capability for manufacturing and final assembly. One word is that as our devices we have to install in offshore are quite large and quite heavy. To optimize the costs, it's really important to have the final assembly really close to the final site, because the offshore means are quite costly. And needs to be transport or manufacture really close to quayside to be able to receive an offshore construction vessel. So now I will present you our first project. So this 1 megawatt turbine is made with 4 turbines of 8 meter diameters, 4 meter high. The total dry weight is 280 tons. And the overall dimension of the turbine is 21 meter long by 12 meter high. And for this first turbine, the fabrication lengths about 20 months, with about 6 months of final assembly in the cement workshop. For this project, we, as Fraser presented, for tidal turbines, which are not floating, we have mainly 2 solutions, which are gravity-based foundation and braided foundation. And same as Atlantis, because of risk and length of operations, and also decommissioning of the site, because we just, for this project, the deployment was only for 1 or 2 years, so we have to decommission quite soon after the deployment. We choose to have gravity-based foundation. So for this project, we had 250 tons gravity foundations. So it's a tripod steel structure you see in the drawings, and in each foot we have cast iron ballast, and the total cast iron ballast of this project is 1,000 tons. So about 300 in each foot. We installed it last April last year with there is a mistake on this presentation, but it was a DP 400 tons vessel. It's a Norman Vision operated by Ocean Installer, and we turned it into operation end of June last year, and from this date we have 91% of availability rates. We also certified the power curve assessment following an IEC standard by Bureau Veritas. So we had this certification fully approved last July, and the schedule is now to decommission and inspect it next summer. So we will have a full 2 years of operation, hopefully. What are the learnings about this first project? Main learnings are about the design, because this design of this first prototype was born from our proprietary design and what we used to design our river and estuaries application. So the main issues with this design is that because of the lateral ducts, we have high environmental loads for angle of incidence higher than 20 degrees, which is possible in extreme environmental case. And these lateral ducts induced to have large horizontal plates, and this induced quite high wave loads. And the total weight, then the issue of that is that the weight of the horizontal plates regarding to the is really high, is quite high regarding to the total turbine weights. It was for this first project about 40%. So for the next, we based on these learnings, we made quite of good improvement in the design of the next generation. And we are now designing and producing a new generation we are calling Ocean Quest 2.5 with a 2.5 megawatt capacity. And for this new generation, so the main improvement are the suppression of lateral ducts and improvement of performance of this turbine by engineering the rotor. And regarding manufacture, there is nothing revolutionary. So I think it's just a classic approach. We are optimizing weights and welding lengths and try to parallelize as much as possible the manufacturing process to optimize cost and schedule. So now next generation, Ocean Quest 2.5. So the next generation is 2.5 megawatts nominal output per unit. And we design it to reach 200 ton dry weight. So we reduced by 80 tons the weight of the turbine. And this allow us to use 250 tons DP vessel and 200 to reduce CapEx and OpEx costs. Yeah, that's it. So this new generation will measure 16 meter high and 21 meter length. This picture shows you the sub-elements of the structure. So this is the ducted structure, which is much smaller than our previous project. And all the elements are made in carbon steel. We have 5 elements. So the lower plate weighs 13 tons, and the upper plates also 13 tons. And you have the dimension, the overall dimension of these elements. The central ducts weighs 13 to 15 tons. And the central plates weighs 23 tons. So this is all made still manufactured, and yeah, that's it. And it's mainly made with plates from 6 to 15 millimeter thickness. We have also water tightened elements to integrate our conversion elements, our electrical system. The diesel pressure is 5 to 7 bars depending on the site location. And the overall dimension is 5.7 meter high to 2.5 meter diameter. And we have 2 elements per turbines. To water tightened elements per turbine. The weight of each is 5 tons. Regarding foundation, for coming project, we are still we still plan to deploy gravity-based foundation. So you have here a picture of our gravity-based foundation, which is made in carbon steel and with an overall dimension of 31 meters by 27 meters and with a total weight of 250 tons. The final assembly needs to be done at quayside, not because we don't. It's really better not to transport it after it's fully finished. And it needs to be done as close as possible to site installation. Our roadmap. We at the moment we are developing a pilot project in Blanchard of 14 megawatts with 6 Ocean Quest 2.5 units, and our schedule is to manufacture the first of this turbine to start the production next summer and to have a field validation in 2022, and then to deploy all the farm, all the array in 2023 to deploy the 6 turbines. And then to have a commercial deployment from 2026. So we had quite a lot of milestone in this Blanchard pilot project, and are really confident in this schedule. To conclude, we have quite a lot of industrial opportunities in France regarding steel manufacture, because on this presentation I really focus on steel fabrication. We have the manufacture of the sub-elements, the water-tightened structures, the manufacture and the assembly of foundation, preferably in Cherbourg for the final assembly. We have also other opportunities regarding mechanical elements, regarding the shafts, the bearings, and some other elements which I didn't mention in this presentation. And regarding industrial opportunities in other Tidal sites, it's more or less the same, and we added to that there is the assembly of the turbines, final assembly of the turbine. So just to conclude, for any information or quotation regarding these various topics, please contact Sébastien Deviller, which is our purchase manager. Thank you very much.
Thank you very much, Raphael. That was very useful, again, insight into the various supply chain opportunities, big and small, associated with your technology. So we've got about 10 minutes left to answer some questions. We'll try and aim for perhaps one question to each of our panelists, or even perhaps the same question to each of our panelists to get some different insights. Theo, did you want to see what questions have come in? I saw one.
Sure. Thanks, James. Yeah, so we've got a question here from Manuel on the Q&A. And he's basically asking, it's aimed at Mark from Orbital. Do you think that the O2 supply chain could be replicated in Asia? And do you think there'll be limitations in terms of equipment or perhaps professional manpower for volume manufacture in future?
Yeah, thanks for the question. No, I think the capabilities in Asia are fairly well known. I think they'll have all the capabilities to do the fabrications that we require on the O2. As usual with these projects, it'll be funding and financing that will effectively set the geographical conditions. But I have no issue that the Asian companies will be able to manufacture the components at all.
Okay, thanks, Mark. I've got another question here from Nathan Wilson, and I think this one was aimed at Fraser. So he touches on here about the transferability of skills, experience. I'd probably like to open that out to maybe manufacturing techniques. And are they transferable across sectors? For example, the wind sector. And what are your thoughts around that, Fraser?
So the Atlantis turbine, when it was assembled down at Blythe, down at the OREC facility down there, I think 3Sun did a lot of the cabling work within the actual assembly of the turbine. So with regards to the kind of capability and knowledge of a wind turbine, yeah, it is directly transferable. One of the things that we've come to realize and understand is that actually people do draw analogies between wind turbines and tidal turbines, and actually they are similar and very different. Our rotation speed varies greatly. It's a lot more like a car than it is a wind turbine in that respect. So rotation speed variations and loading forces, those kind of things are slightly different. But when it comes to the nub of it, it's a 3-bladed, slow speed shaft, gearbox, generator. It is very much like a wind turbine, be it onshore or offshore. So the main shaft seal is off a ship, again for us, and Andritz an SKF system. So there are a lot of analogies that you can draw, and there are a lot of skill sets around Europe that can certainly be transferred straight to tidal without much difficulty.
Great, thank you, Fraser. We've got another question here. I don't know whether I should post it or not, but asking about the implications around Brexit. I mean, ultimately, no one really knows the answer to the question. Will this limit any potential UK supply chain content? I guess we won't know until Brexit has happened. But I notice generally, for example, Orbital Marine Power supply chain was spread across the whole of the UK, and you would look for your devices to be supplied local to the project. Is that a trend similar to all the technologies? So, Raphael, is that the tack that you use for HydroQuest?
Yeah, for sure. Yeah, we are for various. So, as I told in my presentation, we are now working in detail in Rat Blanchard deployment. So we have quite a lot of investigation and trends locally, but we are really open because we have quite, as I present, a lot of opportunities. But on the project we are developing, we really have in mind that it needs to be manufactured locally for the large steel parts and for the final assembly. So yeah, it's very important for us.
Okay, thanks, Raphael. Another question really here is, so at the moment we're deploying, one or two devices at a time of a similar design, perhaps a one-off design in terms of it being the first iteration of your design, and it will evolve as you go on. You've obviously got to balance the idea of scaling up production versus perhaps removing some of the excess safety factors or the built-in redundancy in your devices. I just wondered if I could go around each of the presenters and ask just how are you dealing with that, the change to your design and the removal of that excess, that safety factor versus scaling up the volume production. So could I post that one to Mark or William, please?
And scaling up, really, I don't see as a major issue apart from pure space. We've got specific requirements on the fabrication of the O2 turbine, which are capacity led. So you can do several operations in parallel, have several suppliers which can do key operations. But the problem is when they all start to come together as assemblies, or as Raphael said, you need quayside facilities for when the turbine is fully assembled and then moved out to be deployed. So it's really developing a large number of parallel suppliers is the solution, I think, to high volume manufacture. It spreads the load, spreads the capacity, and also gives you access to more space. Yeah. I don't think our design specifically is affected in any way by that, because the design will always be based along the loads at the important points on the structure. Have you got anything to add, William?
Yeah, no, I think that ties in perfectly with what I was going to say. So the way for us to reduce cost of energy by taking out material, in targeted locations is from understanding of the loads. So the more data and the better the quality of data that we can get back from the devices that we've tested in the past and are going to be testing. It gives us a lot more confidence and certainty about the loads. So we can, at that point, we can then sort of make targeted decisions about where best to remove steel or remove complexity.
Thank you, guys. Fraser, can I post the same question to you, please? Are you using a similar ethos as Orbital Marine, or have you got a different?
No, I'll talk about Atlantis and maybe Hammerfest in that regard. So, having had the Hammerfest turbines now are coming up to 2 years of continued operation subsea. So they've validated their tidal blading model, which is the mathematical unit or mathematical simulation that we use to generate loading and forcing. And it's really cost and risk. So yet we can start taking material out, but in these early units, not having turbines operating or having failures is seen as a perceived higher risk. It's the industry, it really doesn't work. It's like, well, just got the load slightly wrong. So I think having that information now in the bank really starts to push forward on warranties and availability and guaranteeing availability through the contracts. So that's something that's going to come on. And with regards to manufacture, I think that's a question around warranty and a question around who is warranting that turbine going forwards. None of the developers right now have balance sheets that can do that. So that is going to have a significant influence on where those devices are fabricated and developed, depending on who buys them or who warrants them. But yeah, getting materials out, it's just knowing your fatigue life, knowing your factors, and knowing how you operate that turbine, and knowing the site, knowing the turbulence. We've learned a huge amount at Maygen. Understanding the turbulence at the Maygen site. We've been there now for 5 years continual. What are the loads and forces that we designed to, and what are they actually now in the real world, and how do they vary, and what impact does that have? So that's all knowledge in the bank going forwards.
Thanks, Fraser. And Raphael, if I could post that question to you. I know HydroQuest are entering into year 2 at the Pampolbrest site.
Yeah, more or less same for us. Is we may reduce the safety factors in mid-terms deployments by learnings and analyzing our sensors, lifetime, and so on. So as Fraser said, in tidal sites, turbulence is an important input, and so we have to manage it with confidence. And so when we will be able to reduce safety factors, but not that soon. And regarding your question about scaling up, our strategy is just to design the smallest sub-elements as possible and to do the final assembly as quick as possible to be able to scale up as much as possible.
Great. Well,
thank you, Raphael.
And thank you very much to everyone. I think that if there's any other questions, we'll take a note of them and try and get back to you over the next week or so. So just wanted to say thank you very much to everyone for attending today. Thank you very much to our panelists. Just want to say that the full recorded version of the webinar will be available on the Interreg Tiger website. again, just to remind you, this is the second in a series of supply chain events. There'll be a number of others with different themes, such as composites and other supply chain and manufacturing areas as well. We'll be adding the dates to the website regarding those webinars as they become fixed, but do expect to see them over the next month to 2 months. If you want to receive more regular updates, please sign up to our e-newsletter as well. We'll also just be sending a short survey out after this webinar just to get your insights and input on how it worked for you, and any feedback on that would be greatly appreciated. So yeah, so again, just want to say thank you to everybody. Thank you very much for attending, and we'll hope to hear from you again and see you again at future webinar events. Thank you very much.